Hello, good evening, everyone. This is Celso Batalha Choten, and today is Monday, July 10th, and we have an exam going on. So, it's our midterm number two, and it's going to be closed at midnight. And in fact, I will reopen midterm number two. There will not necessarily be the same questions on Wednesday. So you have a second chance to go through and complete your exam. So basically, um, um, I recommend that you do it if you are not well prepared yet, because I will select the highest score of both attempts. How are you doing? Somebody in there? Who is that? Who that might be? Can you hear me? Can you hear me? Yes, I can hear you. But I can see you, Melissa. So you are Melissa. Okay. All right. So I will start now. And I was telling the class that we have an exam going on. And and did you do your exam already? Yes. Okay. All right. Good. Okay. So I will stop showing my face. There you go. And in fact, I could have my face on. It doesn't matter. But I will start with the lecture today. But before I start, do you have any question, Melissa, you want to ask? And your microphone is mute, so I can't hear you. I can see you, but I can't hear you. I can't hear you. I cannot hear you. It seems that your speaker is... Oh, wait a second. Oh, it's my fault. It's my computer.
Okay. Okay.
Okay, I can hear
now?
you. Okay, sorry, that was my
Okay.
fault. Okay, all right, cool. So I will start with... Do you have any question?
No, I just wanted wanted to meet to take some notes before
Okay.
the exam, but yeah.
Okay. All right. So
Thank you.
let's go forward and let me share screen now. And we are pretty much in chapter 10. Let me just make sure I have the means to annotate things. That's not it, what I was looking for. I think that's going to be all right. So chapter 10, it deals with a consequence of chapter 4, which deals with light, basically. So the main point is we learn that light has certain properties, and when light interacts with matter, it matter imprints certain features on light, and then we can read those features, and then we can infer properties of the material that interact with light. So think about, in astronomy, we talk about not only planets in our solar system, but also we talk about exoplanets, as we saw in the previous chapter. We talk about stars, not just the sun, which is somewhat closer, but stars that are so far away that certainly, based on our current technology and age, we cannot visit those stars. We also, in astronomy, we learn in the chapter 1, there are galaxies out there, collections of hundreds of billions of stars, and now we know each star populated by a certain number of planets, and each planets with their own satellites, and so the universe is made of so many components and members that the main question is, how do we know about them? How do you know for sure they exist? And it's not just a myth or just some theory without proving, without the data to back up those ideas. I mean, what are you guys doing? Pretty much doing science fiction or what? Well, chapter 10 is comes to rescue and give us elements to answer this question. We know how light behave, and we know how light interact with matter, and then we can use light that was either produced or interact with these objects that are so far away that in our lifetime and probably in several generations after us, we won't be able to visit. So light emitted by these objects have been traveling through the space for um, thousands of years, millions of years, or billions of years. So, and now, as light arrives in our telescope, we can take this light collected using telescopes, as we learn in chapter 4, I think. So collected these lights using telescopes and detectors, and then take these lights and put in our computers. And then you, as a student, can have the opportunity of using your knowledge about interaction of light with matter to infer properties of objects where the light got to be produced or got to be interacted with. So the main point is, you don't need to visit these places. You just need to collect the light that was in these places. And light itself will bring information about these places. So chapter 10 gives us the tools astronomers use in order to infer stellar properties, basically. And in few chapters ahead, we are using, or we will be using, some of the same tools to infer properties of not only stars but collections of stars we call galaxies, and then we will build up on this knowledge and try to infer properties not just of galaxies but collections and clusters of galaxies. And that's how we know the universe is the way it is. The universe behaves the way it behaves because we have the ability of collecting light and analyze light itself. Hey, Allegra. So let's start with the first property. And in fact, this property was visualized and was invented not recently. It's pretty much ancient. In fact, was devised by ancient Greek philosophers or astronomers, if you will, and that is pretty much called parallax. So basically, what parallax is. So imagine for a brief amount of time that Earth goes around the Sun in a circular path, as you can see over here. So you have a Sun, and certainly this figure is not in scale, which means the Sun, the relative comparison, the relative size of the Sun when compared with Earth is not as depicted here in this yellow ball or this blue ball. The Sun is about 100 times as big as Earth. So certainly this figure is not in scale. But imagine for a while that Earth would go around the Sun in a nice circular path, as you can see in this figure. And imagine there is a star here in the picture is labeled star A. And there is another star, star B, which is somewhat a little further out. And there is a bunch of other stars very far away, so far away that it resembles when you see cows on top of a hill and you are driving through a highway that is very much far away from the hilltop. And you see these cows, they move, but they are so far away that for all purposes, it seems that they are not moving. They are pretty much stationary. But the part of the highway that's next to the asphalt passed by us so fast because it's closer to us. So the main point is, if you think about the sun and Earth system, and a star that's closer to us, and another star that's not so close, a little bit further, and stars that are even far away. As we move around the sun, or going to the highway example, as we drive through the highway, so those features that seem to be closer to us, they seem to be moving past by us with a rate of change in position much more severe than those that are further away. So those stars that are very far away were called by ancient astronomers fixed stars. They thought these stars would be fixed, would be glued against the celestial sphere, and we saw in the beginning of this course, celestial sphere, in fact, it doesn't exist. It's just an imaginary concept ancient astronomers developed in order to explain daily or diurnal motion, as we saw in chapter 2, and other type of motions we also saw in chapter 2. But let's go back to our Earth going around the sun. So let's say that today, we here on the top today, we observe at star A, and as we look at star A with a telescope, we see the star A, and I hope you can see my arrow here. We see the star A projected against a group of stars that are pictured in this diagram down here. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 stars that are so far away. Those are the fixed stars, and we see our star A somewhat projected against that part of the sky. We also today look towards star B, and we see the star B project somewhat in there, in that same region, right? But then look at this. Earth keeps going around the sun. And then 6 months later, the sun is over here. Oh, Earth is down here, below the sun. And then what we do, we look at star A again. So the star A that's closer to us now is saying, kind of a further away. Oh, wait a second. Why don't I have... My computer is getting out of juice. What's going on? Wait a second. There you go. So the star A 6 months later has changed its position. It went from this part of the sky to this other part of the sky. And then if you have a diagram, if you have a piece of paper and you map these fixed stars on a piece of paper, and as you observe over a period of 6 months, you see your star A moving this much in the sky. In your piece of paper, you know how many arc minutes that is. Because you can use, remember in chapter 2, we saw that if we make a fist at arm's length like this, you make a fist at arm's length and project that fist against the sky, the fist will project more or less an angular separation in the sky that is about 10 degrees. So you know what the sky 10 degrees is, so you should know how many arc minutes this little square is. So an astronomer, even a Greek astronomer, thousands of years ago, would be well trained enough to know how many arc minutes or arc seconds this displacement is. Are you all there? Okay. Now comes geometry. Now, you have to go back to Miss, what's the name of your geometry teacher? Miss Parker or whatever. You have to go back to your geometry teacher and remember a little bit of geometry, and that is, if you take, I thought I could have a marker here. My marker is not coming in for some reason. Yeah, I can't mark this figure. So if you know the distance between Earth and the sun, which we know, and if you know this angle over here, And we know this angle because that is given by the separation, the motion of the star in the sky. So if you know half of that angle is equal, according to trigonometry, the distance between Earth and the Sun, and the distance between the Sun and that star. So it's the ratio between this quantity here. Can you see my arrow? Can you see my arrow moving? And this quantity here, which is the distance from the Sun to the sky, to the star. So when you, in other words, you have the ability. Let me bring this one. Not this one. Let me do something here quicker. I think I will be able to do some markers now. Okay. I'm using this just to write so we can follow this. So basically, here's Earth, Sun, so Earth right here, Sun right there, and there is a star somewhere here. And because we know the apparent motion of the star in the sky, we call parallax, which is half of this angle here. So this angle, which we know we can measure in the sky, is equal to the distance between Earth and the Sun, which is 1 astronomical unit. This is equal to a certain amount of miles or kilometers divided by the distance between the Sun and the star. In other words, the distance to a star is equal to 1 astronomical unit. That's some math, some simple math, divided by that angle. So what I want to show you is this. Ancient astronomers knew of this mathematics, and they didn't know the distance of Earth to the Sun, but they knew they could find the distance to a close star if they knew how to measure this angle. They were not able to measure, there was no technology. But nowadays, since the 1800s, this technology exists, especially with the telescopes and with the space telescopes. These angles, the angle in which stars apparently move as we circle the sun, is called, and it gives the parallax of the stars, allow or enable us to measure distance. In other words, we can find distance to stars without using rulers or going to the stars itself. We just observe them and use a simple geometry. Okay? Got it? That is the so-called parallax. Now, another set of terms in this chapter, that's chapter 10, that you should be able to learn to distinguish is the difference between what brightness is and what luminosity is. So for now, and for us, brightness and apparent magnitude will represent the same thing. It's a measure of how bright stars are in the sky as we see it. In other words, let's say we go outside at night, 10 p.m., look up to the stars, and then we see some of them pretty bright, some of them very dim, and some of them we don't see it. So there is a whole range of brightness in there. And the question arises is, okay, why there are those differences in brightness? So why stars have different brightness? So you could come up with several answers. Answer A, well, because they are at different distance from us, right? So the stars, they are very dim, they are very far away. The stars, they are very bright, they are close to us, like the sun. The sun is the brightest star in the sky, so bright that prevents and washes out all the other stars that happen to be visible at the same time of the day, and the sun is in the sky. We don't see it because the sun is too bright. So it could be distance. But also somebody could claim, well, if a star is small and you compare with the star that's giant, the giant stars will appear to be brighter than the smallest star. Okay, so this chapter will lead us to first identify one important term, and that is luminosity. And that's over here, luminosity. So luminosity is not brightness. The luminosity of a star is a measure of the amount of energy the star itself produces and sends out to space. So some of the stars might be gigantic. Some of the stars might be very small in size. Like the sun is not a giant star. The sun is a star of a relatively small size. There are stars that are 100 times bigger, 1,000 times bigger, several times of thousands of times bigger than the sun is. And some stars are much smaller than the sun. The sun is somewhat in the middle range. So, but somebody could also claim the following information, and that is, well, some stars are cool stars, which means, as we study in chapter 4, the cool stars happen to be associated with a gas that is producing primarily reddish radiation. And stars, they are very hot, they are producing bluish radiation. So if you take two stars that have the same size, but one is much hotter than the other, the hottest star will produce more energy than the coolest star. So the main point when we learn about brightness and luminosity is a measure of energy the star produces, and that measure depends on two important quantities. And those are temperature, temperature and size. So in a sense, hot stars and big stars and hot, they tend to be luminous. And cool stars and small stars, they tend to be, as we call, subluminous. Sorry, the mess here. I didn't know why I couldn't write in that paper. But there is an important relation in chapter 10. See if I go to the end here so I can use an empty space. In chapter 10, there is an important ratio that we are going to learn, and that is brightness of a star. The brightness of a star is equal to the luminosity of the star divided by a number, 4 times pi times the distance to that star squared. This equation is called the inverse square law. Oh my goodness, what a bad handwriting. There you go. Inverse square law. So what is this equation? Why this law is so important for us? The inverse square law tells us that we know how light propagates, which means if you have a source of light like a light bulb that has 100 watts of power, so it's producing 100 units of energy every second, right? So that's 100 watts. It's a very bright light bulb. So if we have this light bulb close to our face, first of all, it's going to be hot. Second, it's going to be very bright. But when we take this light bulb and put, let's say, 10 meters away from us, it's not going to be as hot, and certainly it's not going to be as bright. And if we turn off all the lights and put this light bulb on top of a mountain, we might still be able to see something, but not as much as it was 10 meters away, and certainly not close to our nose. So what's going on here? So what's going on is the same process, the same physical law that govern the idea. If you are talking to somebody very close, you can hear well. But when that person goes away from you, the intensity of the sound goes down. And the intensity falls with the same law. It's the square of the distance. The intensity of a sound wave and the intensity of waves in general falls with the square of the distance. And you can measure this in the laboratory. You can use equations of physics to determine that. Why this equation, why this law is so robust, is so magnificent for us astronomers? So look at this. So brightness, the amount of energy you receive here on Earth, is something that is very simple to measure. You can measure with telescopes. So which means if you have good telescopes and if you have a good set of detectors, if the sky is clear, you don't have clouds, you don't have any impedance, you take your telescope, you point the telescope to the star, and then you measure the amount of brightness of that star. You measure this quantity over here, right? You have a number, right? Now look at this. Imagine you have some information about that star. Imagine you're observing a star that for all purposes is very much similar to our sun. So we know how luminous the sun is. We know how much energy the sun is producing over a certain period of time. So we have access to this quantity luminosity. In other words, we know this because we observe, and let's say we happen to find tools to determine L, the luminosity, the amount of energy the object itself is putting out in the space. What can you determine? The distance. So the inverse square law is one of the most robust expression in astronomy, because if you happen using different methods, if you happen to collect information about the amount of energy the star or the galaxy or whatever you're studying or the cloud is emitting in space, so you know L, you observe B, you can get D, the distance. You know the distance to your object. And since late 1800 and early 1900, astronomers start mapping the universe that way. They start observing objects, and since by applying the inverse square law, they initiate a process of mapping out our galaxy, our local group of stars, our local group of galaxy, and now we have a perfect picture and 3D picture of our universe, at least the universe we claim to be the visible universe, using solely this simple equation, which is the inverse square law. Okay. The last thing I would like to go, I don't want to keep you too long, is to invite you to a website. Where is it? Just a second. Was my what was here? Oh, there you go. This website I show to the class in the chat last week. You do a Google on NAP, let me go, NAAP, Astro Labs. And then you're gonna go to this place, and Nebraska Astronomy Applets, and you go to class actions. That's what we want to do. And there are all kind of things. If you want to learn astronomy, is an excellent, fantastic resource. But that's not what I want to show. There you go, simulations. There you go. These are all the simulations, and in fact, our book, Understanding Our Universe, it sends several links to exactly these simulations, and it's an important tool. And this chapter 4 chapter 10 introduces stars as black body. So what black body is? So black body is an object that has the ability of absorbing radiation, absorbing energy in all possible frequencies. And when a like a beam of light is shined upon this object, it takes that energy, and instead of reflecting in the same frequency, which means let's say you shine a green laser on that object, right? And then you expect that object is going to reflect back green laser. It doesn't. It takes that energy in the green color band and then distributes that energy in the all possible colors. But it distributed in such a way, in such a distribution we call black body distribution. It's a Planck function. It's a black body distribution, and I show you in a little bit. So the book emphasizes the relation there is between the intensity of these curves and the color the object itself presents itself. So why is that? The reason to that is the stars, in good extent, they are black body. They behave like black body. In other words, stars have the ability of producing their own energy, and we are going to learn this. I think tomorrow. That's going to be the point of the talk, and we are discussing the subject in star formation. So stars have the ability of producing their own energy as a result of fusion reaction in their very core. So that energy is produced by the star. So the star do not reflect the light from anywhere. It's within. It's from their own internal system. Which means when you look at this light source, you see it as a black body, except by absorptions that happen in the atmosphere that break down that curve, but it's pretty much close to a black body. So let me show you the first property. And this is very well explained in this simulation here. Imagine you have a circuit that what you do, you increase the temperature, right? The temperature, which basically you have a circuit here with current, and the current goes through this nail, and this nail start to heat up, and as the nail heat up, the color will change, eventually to the point that it will melt. So let's start the animation and then you see. Now is the temperature and the color this black body is producing. The temperature increase, the black body color is changing to the point that eventually it's gonna melt. And when it melts, the circuit closes, right? And then the black body curve that you can see here on the right-hand side is start to change it, okay? And you see its behavior, its shape changing as we see over here. So this graphic is a graphic of peak intensity, which means the intensity, the distribution of this energy, and wavelength. I like to call wavelength in our astronomy 10 course which is pretty much introductory. This is not a physics course. I like to call wavelength as color. So 300 nanometer color is ultraviolet, basically. 700 nanometers infrared or near infrared. So we have the green color for 100 nanometers, kind of a bluish. This is an orange at 600 nanometers. And white light is a combination of light of all these different frequencies here. That's what white is. White is not a specific color, as black is not a specific color. Black is, in physics, the absence of the absence of any sort of radiation, and that's why in physics we use we use a lot the word black or dark to indicate part of knowledge we don't know yet. There is no light on it yet, so we haven't figured out yet. And also, is the exciting part of doing science is when we don't know something and we want to know it, and so there is no point of comparison, right? If I mean my room, I have a room here. In fact, I'm the room of my son, so I can look at things and I can see his medals, I can see his bed and his pictures and a fan, my cup, because I had coffee last. In fact, is a cup with ice cream from last night. I'm very sloppy. So I mean, I identify those things. Why? Because there is light here, right? And then my memory banks identify these symbols, and then I know what they are. Okay, I know because I can see them. Now imagine I turn off all the lights and I shut down my window and completely in dark. I can't see anything. There's no way. You can't see. You don't recognize anything. And that's the beauty of part of knowledge in science when we don't know. Because that's the point that you start to investigate and to advance into aspects of knowledge you don't know, you haven't figured out yet. And that's the exciting part of science. So in science, we have black body, dark matter, dark energy, black holes, dark dwarfs, and so on and so on. And black body is one of the examples. So I will repeat this, and just to show in the very beginning, there is no light source at all, right? The environment is dark. We don't see anything. And when the object becomes self-luminous, then you see colors. But as it gets hotter, the color migrates from red to the blue. And if you were in an environment, like a star environment, it would eventually vaporize and becomes what we call plasma. Plasma is a bunch of ions, and the gas must be a very high temperature. So here's an example of black body. And here's an example of absorption and emission lines. So this is part of one of the tools of astronomers, we call spectroscopy. And you might have read that in your book. So what spectroscopy is? Spectroscopy is the following thing. And let me show you by another example showing the atom. So an atom, like hydrogen, this is an atom of hydrogen, at least a representation of it. So you have a proton in the nucleus, an electron that goes around, and all these lines here represent what we call orbitals, which means regions around the nucleus that one electron could be more likely found in these regions. So Mother Nature is kind of funny. Mother Nature doesn't like electrons in the region between the orbitals. When you go to our universe here, right, our size and the size of the solar system, you can find planets at any position beyond the sun. You can have planets where Mercury is, or in the region between Mercury and Venus. It doesn't matter. But when you go to the atomic level, it seems that nature flip it over and say, hey, those laws that govern the macro universe will not govern the micro universe, the subatomic particles. And the laws, and pretty much those laws are governed by quantum mechanics. So quantum mechanics say, hey, electrons cannot exist in between those orbitals, first of all. So look at an example. Imagine this is an atom that is minding its own business, and then you shoot a particle of light on it. It's not going to do anything. You can shoot as many as you want, and these particles of light will just pass by the atom and do not bother. But look what I'm going to do. I'm going to shoot a photon that has a color, that has a wavelength, that is just good enough to take this electron from this orbital and send it right here. Okay? So that's what I'm going to do. I'm going to send this photon. And now the electron jumped and it's going to fall back. So these laws exist in the subatomic level, and that's how I start talking today, the lecture. So in this, we know about quasars, stars, and exoplanets, everything that's going on above our beyond our solar system because of light. Now, light interacts with atoms in stars and galaxies and quasars and black holes, vicinity of black holes. And as it does, it gains some information. And that information is imprinted in light itself, and then we observe, and then we draw conclusions of it. So I could, for instance, send out a different photon, like this one, more energetic, and be able to send the electron to a further away orbit, and eventually the electron cascaded down, sending out a photon and sending out another photon. So that interplay of energy leads what in our book now is called continuum, which is the rainbow you can see, or a set of emission lines like those of hydrogen or helium, or ionized helium, hydrogen, like molecules, metals, and ionized metals. So which means metals, hydrogen, molecules, when light interacts with them, it gives traces we call lines, and these lines are unique of these elements, so that if you point your telescope to a cloud and you see these three typical lines, one is very blue, the other is somewhat blue, the other one is cyan. I mean, we know which element those lines correspond to. And then we can say, okay, that cloud over there has helium, or that cloud over there has some magnesium, if we are talking about metals. We can look at stars, for instance, like a very hot star, like an O star. And if we observe an O star, we will see those three lines there, and they are helium lines. If you observe, for instance, A stars, we certainly will find hydrogen lines on them. And these lines are typical of hydrogen. We can study them and analyze them in the laboratory. So spectroscopy, which was developed late 1800 and early 1900, is one of the most significant and important tools astronomers have nowadays that allow us not only to measure the chemical composition of stars and galaxies, but also by analyzing how deep and how asymmetric sometimes these lines are, what sort of bumps and features they have, we can infer not only the chemical composition, but also if there are rotation going on, if there are magnetic activity going on, if there are some specific interaction with a companion, all kind of informations can be derived using spectroscopy. Like in CSI investigation, those crime scene investigation, this type of shows with a lot of blood, those are good. So sometimes they go to a crime scene and there is some smell of a perfume, and they take a sample of it, they go to the laboratory. Exactly what they do, they take that sample of material and they vaporize, they create a vapor. and then they shine a light on it, and the light interact with the vapor, creating these trace lines. And then somebody who studied um, perfumes and molecules and all the different molecules that lead to different type of perfume, that person can identify which perfume that is. Spectroscopy done, in a local ground, and so that can be also why not apply to stars, and that's how we know about stars. We don't go there, we don't visit them, but they visit us all the time, and they bring us light they produce, and by studying these lights, we can learn about them. So I don't want to keep you too long. I like this to be on 45 minutes. Again, this Doppler shift, this is important. Doppler shift is one of the most important technique used by astronomers, especially now that we are studying exoplanets. And one of the technique used to find exoplanets is the Doppler shift. So Doppler shift is based on the relative start emission. So let's say you have a source that is producing certain type of radiation or light, and then an observer like us move towards that source. So look what happened with the wavelength, with the distance between the crests of these waves. It becomes shorter. So the frequency increases, the pitch goes up if you are talking about sound waves. And when you move away, look what happened with the distance between crests. It increases. So we call that red shift. We call that a decrease in the pitch of the sound waves, if these were sound waves. So Doppler effect is based on the relative velocity between source and observer. And the faster the source moves or the observer moves towards or away from the source, the shorter or the higher the observed frequency is. So astronomers using Doppler effect for everything to find out the characteristics of orbital motion between two stars, or how the behavior of clusters of stars or clusters of galaxies. We use the Doppler shift technique to determine how fast the universe expands. The universe expands, and if we are going to study dark energy in the future. Dark energy was found as a result of a direct application of a Doppler effect. If you ever got a speeding ticket, the technique used was Doppler effect. Somebody shoot a infrared light beam on your car that reflect back to the officer, and by comparing the frequency sent and the frequency received, the officer could, the computer could give you the speed, and there is no dispute there, no dispute at all. So probably 10 years ago with the radar, you could dispute. Now with the laser, you cannot. It shoots exactly to your car. There is no claims there. Better pay the tickets and be done with. All right. Okay, Melissa, any question? Melissa, we're sleeping.
No, I'm here. No, I don't have no.
All right. Okay. All right. So I stop taping now, and wait a second.